For most of human history, the speed of light has seemed like one of nature's simplest facts. It is measured with astonishing precision, written into textbooks, built into every satellite navigation system, and woven into every modern description of the cosmos. We learn that light travels at nearly 300,000 kilometers every second, and before long the number begins to feel almost ordinary, like the distance around the Earth or the number of hours in a day. Yet beneath that familiar certainty lies a question that receives surprisingly little attention. We often ask how fast light travels. We rarely stop to ask why it travels at that speed in the first place. The distinction appears subtle at first. Measuring something is one challenge. Explaining why nature has chosen that particular value is another entirely. A ruler can tell us the height of a mountain, but it cannot explain why the mountain exists in much the same way. Countless experiments have confirmed the speed of light with extraordinary accuracy, while the deeper reason for that value remains far less obvious. Modern astronomy depends upon this constant in ways that are easy to overlook. Every image captured by a space telescope, every signal received from a distant spacecraft, every glimpse of an ancient galaxy arriving from billions of years ago shaped by the same invisible limit. Light does not merely illuminate the universe, it determines how information itself can move across space. It influences the lives of stars, the growth of galaxies, the behavior of black holes, and even our understanding of time itself. What makes this even more intriguing is that physics does not treat the speed of light as simply the speed of one particular kind of wave. According to Einstein's theory of relativity, it is woven into the fabric of space-time itself. Nothing carrying information has ever been observed to travel faster. Cause always precedes effect because this cosmic limit exists. Remove it, or change its value, and the architecture of reality would be profoundly different. But this realization only deepens the mystery. If the speed of light shapes the structure of the universe so completely, where does it come from? Is it an arbitrary number that nature simply happens to possess? Is it a consequence of deeper physical laws that we have not yet uncovered, or could it emerge from an even more fundamental layer of reality? One that modern physics is only beginning to glimpse. These are not questions of philosophy alone. They sit quietly at the frontier of contemporary science, where astronomers, physicists, and cosmologists continue searching for clues hidden within the oldest light in the cosmos, the smallest particles ever observed, and the deepest mathematical descriptions of space-time. Our journey begins with something familiar, the light that reaches our eyes every day. Yet before long, that familiar companion will lead us into one of the most profound mysteries in all of physics, where a number that appears fixed and certain may conceal an answer that humanity has not yet found. And if the speed of light is not merely a measurement, but a window into the deepest laws of the universe, what else might it be trying to tell us the moment we open our eyes each morning? Light has already begun telling us a story. It carries the colours of the sky, the outlines of distant hills, the texture of a familiar room. It reflects from every surface around us before reaching our eyes, allowing our brains to reconstruct a world that feels immediate and continuous. Yet every ray of light, no matter how ordinary it seems, has been travelling. Even the sunlight warming the Earth at this moment began its journey about 8 minutes earlier, leaving the surface of the sun long before it reached our planet. Astronomy extends this simple observation to an almost unimaginable scale. Every star we see belongs to the past. The nearest star beyond the sun, Proxima Centauri, is more than 4 light-years away. Its light began travelling toward Earth over 4 years before it arrived. The great spiral of the Andromeda Galaxy appears to us as it existed more than 2 million years ago. The most distant galaxies ever observed reveal the universe as it was when it was only a small fraction of its current age. In this sense, astronomy is unlike any other science. It never observes the present. It studies history, carried across the cosmos by light. This realization naturally introduces one of the most useful ideas in astronomy, the light year. Despite its name, a light year is not a measure of time but of distance. It is simply the distance that light travels through empty space in 1 year. Nearly 9.46 trillion kilometers, Such enormous units are necessary because the universe is vast beyond everyday intuition. Kilometers become impractical long before we leave our own stellar neighborhood, but this enormous distance depends upon something remarkably consistent. Every measurement assumes that light travels through the vacuum of space at exactly the same speed, approximately 299,792 kilometers every second. This value, often represented by the letter C, appears throughout modern physics with extraordinary regularity. It governs the equations of electromagnetism. It appears naturally in Einstein's theories of special and general relativity. It defines how quickly cause can influence effect across the universe. Today, it is so fundamental that scientists no longer define its value by measuring it. Instead, the meter itself is defined using the speed of light. Distance has effectively been anchored to one of nature's most reliable constants. That reversal is remarkable. For centuries, people measured the speed of light. Now we measure length using light. This confidence did not emerge overnight. It grew through generations of increasingly precise observations. Early philosophers often believed light traveled instantaneously, if sunlight appeared the moment the sun rose. Why suspect otherwise? The immense distances involved made any delay impossible to notice with ordinary experience. Even Galileo, who attempted one of the earliest experiments by uncovering lanterns on distant hillsides, found no detectable delay. The conclusion was not that light had no speed, but that if it did, it was simply too fast for available instruments. Only later would astronomy itself provide the first convincing measurement. In the 17th century, careful observations of Jupiter's moon, Io, revealed tiny differences in the timing of its eclipses. When Earth moved farther from Jupiter in its orbit, the eclipses appeared slightly delayed. When Earth moved closer, they occurred earlier than expected. The Danish astronomer Ole Rømer realized that these changing delays could not be explained by the moon itself. Instead, the light carrying the information required additional time to cross the greater distance. For the first time, light revealed that it did not move infinitely fast. It possessed a measurable speed. Over the centuries that followed, increasingly sophisticated experiments refined that measurement. Rotating mirrors, spinning-toothed wheels, interferometers, lasers, atomic clocks, and eventually satellite technologies all pointed toward the same astonishing conclusion. Every improvement reduced uncertainty, yet the measured value remained unchanged. Few quantities in science have survived so many independent tests with such remarkable consistency. Modern astronomy depends completely upon this reliability. When astronomers determine the distance to nearby stars using parallax, they combine geometry with the predictable behavior of light. When they analyze the spectrum of a distant galaxy, they rely on photons carrying precise information across billions of years. When radio telescopes synchronize observations across continents, they assume that electromagnetic signals obey exactly the same cosmic speed limit. Even the global positioning system quietly depends upon this constant. Signals from satellites race toward receivers on Earth's surface at the speed of light. Tiny differences in travel time, often measured in billionths of a second, reveal a receiver's position, without accounting for light's finite speed and the relativistic effects that accompany it. GPS errors would accumulate by several kilometers each day. The speed of light is therefore not merely an interesting number in a physics textbook. It is the invisible thread connecting nearly every precise measurement humans make of space and time. As our understanding deepened during the 19th century, another realization emerged. Light itself was not unique. Radio waves, microwaves, infrared radiation, visible light, ultraviolet rays, X-rays, and gamma rays all belong to one continuous electromagnetic family. They differed in wavelength and frequency, yet in empty space they all travelled at exactly the same speed. This was one of James Clerk Maxwell's greatest insights. His equations predicted that electric and magnetic fields could sustain one another, producing self-propagating waves. Even more remarkably, the speed predicted by those equations matched the measured speed of light. The conclusion was elegant. Light was an electromagnetic wave. For many physicists, the mystery seemed nearly solved. The equations worked beautifully. Countless experiments confirmed them. Electromagnetism explained reflection, refraction, polarization, interference, and a vast range of natural phenomena. It appeared that science had finally uncovered what light truly was. Yet hidden within this triumph was a question that few initially recognized. Maxwell's equations predicted a speed. They did not explain why the fundamental properties of empty space produce precisely that speed. Why should the electric and magnetic properties of the vacuum possess exactly those values? Why should the universe contain this particular cosmic limit rather than another? Why should every observer, regardless of motion, ultimately agree on the same fundamental constant? The more confidently scientists measured the speed of light, the more quietly another mystery grew beneath it. Perhaps knowing how fast light travels was only the beginning. Perhaps the deeper question had been waiting unnoticed all along. The more accurately scientists measured the speed of light, the more complete the picture seemed to become. By the end of the 19th century, many physicists believed they were approaching the final chapters of their discipline. Newton's laws explained the motion of planets and falling apples alike. Maxwell's equations united electricity, magnetism, and light into a single elegant framework. The heavens appeared orderly. Nature seemed to obey a small collection of universal laws that could, in principle, explain almost everything. It was an era of remarkable confidence, and yet, hidden within this confidence, there were small cracks that few initially recognized. One of the first appeared almost as a philosophical question. Every wave that people had ever encountered required something to travel through. Ocean waves moved through water. Sound waves moved through air. Seismic waves traveled through rock. If light was also a wave, what exactly was waving? The answer seemed obvious. There must be an invisible medium filling all of space. Physicists called it the luminiferous ether, unlike ordinary matter. The ether was imagined to be extraordinarily unusual. It had to be perfectly transparent, so that starlight could pass through it without noticeable resistance. It had to permeate every corner of the universe, even the emptiest regions between galaxies. It had to be rigid enough to support waves traveling at nearly 300,000 kilometers every second, yet so intangible that planets could move through it without slowing down. To modern ears, the ether sounds strange. To scientists of the 19th century, it sounded unavoidable. Without such a medium, it was difficult to understand how a wave could exist at all. The idea quietly settled into textbooks. Very few questioned it, but astronomy had already begun planting seeds of doubt. As Earth circles the Sun at roughly 30 kilometers per second, it constantly changes its direction of motion through space. If the ether truly filled the cosmos like a vast invisible ocean, then Earth should be moving through it, much as a ship moves through calm water. That movement should produce an ether wind, just as someone riding a bicycle feels air rushing past. Earth's motion through the ether should slightly alter the measured speed of light depending on the direction in which it was observed. Light travelling into the ether wind should behave a little differently from light travelling across it. The expected difference was tiny, but by the late 19th century, experimental techniques had become precise enough that many physicists believed they could detect it. If successful, they would not only measure Earth's motion through the ether, they would discover the very substance carrying light itself. In 1887, two American physicists, Albert A. Michelson and Edward W. Morley, built one of the most sensitive scientific instruments ever constructed up to that time. Its principle was beautifully simple. A beam of light would be divided into two identical paths, each travelling at right angles to the other. After reflecting from mirrors, the beams would reunite. If one beam had travelled slightly faster than the other because of Earth's motion through the ether, the returning waves would no longer line up perfectly. Their interference pattern would shift by a tiny but measurable amount. The instrument was extraordinarily sensitive. Even minor differences in travel time could, in principle, be detected. The experiment was repeated. The apparatus was rotated. Measurements were taken at different times of day. Different seasons were considered as Earth changed its direction around the Sun. Everything suggested that an ether wind should eventually reveal itself. Instead, something astonishing happened. Nothing appeared, no matter how carefully the measurements were performed. The expected shift refused to emerge. Light behaved as though Earth were perfectly at rest, or perhaps even more strangely, as though the ether itself did not exist. At first, many physicists assumed the experiment must be incomplete. Perhaps Earth somehow dragged the ether along with it. Perhaps the ether possessed properties no one had anticipated. Perhaps subtle experimental errors remained undiscovered. New explanations multiplied. New experiments followed. Yet the central puzzle refused to disappear. Each improvement produced essentially the same result. No detectable ether wind. No preferred direction in space. No evidence that light required an invisible cosmic medium. It was one of the most uncomfortable situations in science. The equations describing light worked magnificently. The explanation for why they worked no longer seemed convincing. Sometimes, the most profound scientific revolutions begin not with a dramatic discovery, but with a stubborn absence. Scientists expected to find something. Instead, nature remained silent. This silence forced an increasingly uncomfortable question. What if the assumption itself had been wrong? Meanwhile, another difficulty was quietly emerging from an entirely different direction. When astronomers observed starlight passing through telescopes on Earth, they noticed an effect called stellar aberration, discovered by James Bradley in the 18th century. Stellar aberration causes the apparent positions of stars to shift slightly over the course of a year, because Earth moves through space while light is travelling toward it. The effect resembles walking through falling rain, even if the rain falls vertically. A moving observer tilts an umbrella slightly forward because of their own motion. Similarly, telescopes must be tilted ever so slightly in the direction Earth is moving to collect incoming starlight. Stellar aberration confirmed Earth's motion through space with exquisite precision. Yet it did not behave quite as the ether hypothesis naturally predicted. Instead of revealing a simple interaction between Earth and a stationary medium, the observations hinted that light obeyed deeper geometric principles. The pieces no longer fit together as neatly as they once had. Elsewhere, another puzzle was developing inside the atom itself. Experiments studying heated objects showed that classical physics could not correctly predict the colours emitted by hot matter. The equations failed catastrophically at very short wavelengths, producing what later became known as the ultraviolet catastrophe. Maxwell's theory remained extraordinarily successful, but cracks were beginning to appear at its edges. The universe seemed to be whispering that something fundamental was missing. Not only did the ether refuse to reveal itself, classical physics itself was beginning to strain under observations it could not fully explain. These problems appeared unrelated. One involved light travelling through empty space. Another concerned glowing metal. Others emerged from atoms. Still others arose in astronomy. At first glance, they belonged to different branches of science. Only much later would physicists realize they were all pointing toward the same deeper transformation. Nature was asking them to rethink ideas that had seemed unquestionable for centuries. Perhaps space was not the passive stage everyone had imagined. Perhaps time itself was different from common intuition. Perhaps light was not simply another wave moving through an invisible substance. And perhaps the universe was built upon principles far stranger than anyone had dared to expect. The familiar picture had not collapsed. It still described countless observations with extraordinary accuracy. But now there were enough cracks to glimpse something beyond it. The challenge was no longer improving existing theories. It was discovering an entirely new way of thinking about reality itself. The answer would arrive from an unexpected direction, carried not by a more powerful telescope or a larger laboratory, but by a simple question about what it would mean to travel alongside a beam of light. At the close of the 19th century, physics stood in an unusual position. Its greatest achievements inspired extraordinary confidence, yet its most careful experiments had begun producing deeply uncomfortable questions. The equations describing light were among the most successful ever written. They explained electricity, magnetism, radio waves, and visible light with astonishing accuracy. Engineers used them to design telegraphs, generators, and the first wireless transmitters. Astronomers relied upon them to interpret the light of distant stars. But beneath their elegance, one question remained unresolved. If light was a wave, what was waving? For decades, the ether had seemed the obvious answer. The Michelson-Morley experiment had failed to detect it. Yet many scientists still believed some modified version of the ether must exist. After all, abandoning the idea entirely felt almost impossible. Waves without a medium seemed to contradict everyday experience. Rather than discard the ether, physicists searched for increasingly elaborate ways to preserve it. Among them was the Irish physicist George Francis Fitzgerald. In 1889, he proposed a remarkably bold idea. Perhaps objects moving through the ether physically contracted in the direction of their motion. If the measuring instruments themselves became slightly shorter as they moved through the ether, the expected changes in the speed of light might disappear independently. The Dutch physicist Hendrik Lorentz developed a similar mathematical description. His equations showed that if moving objects contracted by just the right amount, the puzzling experimental results could indeed be explained. It was an ingenious solution, but it carried an uncomfortable implication. The contraction seemed less like an explanation than a carefully designed adjustment, introduced to rescue an idea that observations increasingly refused to support. Lorentz himself recognized this unease. His mathematical transformations worked beautifully. Yet they still assumed that an invisible ether existed beneath everything. The equations described what observers would measure, but not necessarily why nature behaved that way. The mystery remained. Then, in 1905, a young patent examiner in Bern approached the problem from an entirely different direction. Albert Einstein was not working in one of Europe's great universities. He had no prestigious laboratory and supervised no large research team. Much of his scientific work was done during evenings and weekends, while reviewing patent applications for electrical devices. Yet sometimes a scientific revolution begins not with better instruments, but with better questions. Einstein asked himself something deceptively simple. What would happen if someone could travel alongside a beam of light? According to Maxwell's equations, light is an oscillating electromagnetic wave. If a person could move beside that wave at exactly the same speed, the oscillation should appear frozen, like ocean waves suspended in place. But Maxwell's equations allowed no such stationary light wave. The mathematics simply did not permit it. There was a contradiction hiding within the foundations of physics. The laws describing motion suggested one outcome. The laws describing light suggested another. Einstein became convinced that the problem did not lie with light. Perhaps it lay with the assumptions people made about space and time themselves. For centuries, following Isaac Newton, physicists had treated space as a vast, unchanging stage. Time flowed uniformly everywhere, independent of the events taking place within it. Two observers moving differently might disagree about where something happened, but they would always agree about when it happened. Time was absolute. Einstein questioned this assumption. He proposed two remarkably simple principles. The first was that the laws of physics are the same for every observer moving at a constant velocity. The second was even more startling. The speed of light in a vacuum is the same for every observer, regardless of how fast the source or the observer is moving. At first glance, this seems impossible. If a train moves toward you while sounding its whistle, the sound reaches you differently because your motion and the train's motion combine with the speed of sound through air. Everyday experience teaches us that velocities add together. Shouldn't light behave the same way? Einstein realized that if the speed of light never changes, then something else must. It was not light adjusting to the observer. It was the observer's measurements of space and time adjusting to preserve the speed of light. This was the birth of special relativity. The consequences were extraordinary. Two observers moving relative to one another could disagree about how much time had passed. They could disagree about the length of an object. They could even disagree about whether two distant events happened simultaneously. Yet both observers would measure exactly the same speed of light. The familiar concepts of space and time, once thought completely separate, merged into something far richer. Later, the mathematician Hermann Minkowski described this new picture as space-time, a four-dimensional fabric in which space and time are inseparably woven together. In this new framework, the speed of light was no longer merely the velocity of an electromagnetic wave. It became one of the fundamental conversion factors linking space and time themselves. This was a profound shift in perspective. For generations, Physicists had searched for the medium carrying light. Einstein's theory suggested that no such medium was necessary. Light did not require an ether because it was not moving through a hidden substance in the way sound moves through air. Instead, its constant speed reflected the geometry of space-time itself. The Michelson-Morley experiment suddenly made sense. There had never been an ether wind to detect. The experiment had not failed. It had quietly revealed that one of humanity's deepest assumptions about nature was mistaken. As elegant as this new picture was, science demanded more than elegance. It demanded evidence. Fortunately, evidence soon arrived. Experiments repeatedly confirmed the strange predictions of special relativity. Fast-moving particles created in Earth's upper atmosphere survived longer than expected because their internal clocks slowed relative to observers on the ground. This phenomenon, known as time dilation, is routinely observed in muons produced by cosmic rays. Atomic clocks carried aboard aircraft and satellites tick at slightly different rates than identical clocks on Earth's surface, exactly as relativity predicts. Particle accelerators routinely push electrons and protons to speeds astonishingly close to that of light. As their velocity increases, adding more energy no longer produces proportionally greater speed. Instead, the particles gain energy while remaining forever below the cosmic limit set by c. No experiment has ever accelerated an object carrying mass to the speed of light. The closer such an object approaches that limit, the more energy is required. The required energy rises without bound. Light itself, however, is different. Photons, the quantum particles of light, possess no rest mass. They are not accelerated up to the speed of light. They simply exist travelling at that speed through the vacuum. This distinction would become increasingly important as 20th century physics developed. Einstein's work explained why every observer measures the same speed of light. It transformed our understanding of motion, time, and causality. Yet it left another question quietly waiting in the background. Special relativity accepts the value of c as one of nature's fundamental constants. It explains the consequences of that constant with extraordinary success. But it does not explain why that constant has the value it does. Why should space-time possess precisely this invariant speed? Why not twice as fast, or half as fast, or some entirely different value? Einstein had shown that the speed of light was woven into the fabric of reality. The next mystery was even deeper. What gives that fabric its remarkable properties in the first place? Einstein's theory resolved one of the greatest puzzles of 19th century physics. The ether quietly disappeared from scientific necessity. Space and time were no longer fixed backgrounds against which the universe unfolded. Instead, they became active participants in the story of reality. Distances could change. Time could stretch. Events that seemed simultaneous to one observer might not appear so to another. Yet as revolutionary as this new picture was, it did something unexpected. It shifted the mystery rather than eliminating it. Instead of asking what medium carries light, physicists began asking a deeper question. What exactly is space-time itself? For much of history, space had been treated almost like an empty container. Objects occupied it. Light crossed it. Planets moved through it. But the container itself was assumed to be passive, unchanged by the things inside it. Einstein's next great breakthrough would overturn that idea as completely as special relativity had transformed time. In 1915, after nearly a decade of intense mathematical work, he introduced the general theory of relativity. If special relativity explained motion through flat space-time, general relativity explained what happened when gravity entered the picture. The familiar image of gravity had long been inherited from Isaac Newton. According to Newton, every object possessing mass attracts every other object through an invisible force acting across empty space. The greater the mass, the stronger the attraction. The farther apart two objects are, the weaker the force becomes. For more than 2 centuries, this description explained the motions of planets with extraordinary success. But Einstein proposed something far stranger. Gravity was not a force pulling objects through space. Gravity was the geometry of space-time itself. Mass and energy tell space-time how to curve. Curved space-time tells matter how to move. Although this statement has become famous, its true meaning takes time to appreciate. Consider an aircraft flying across the globe. To the passengers, the route may appear curved on a flat map, yet the aircraft is actually following one of the straightest possible paths across Earth's curved surface. The apparent curve exists because the surface itself is curved. Einstein suggested that planets move in much the same way. Earth is not being pulled around the sun by an invisible rope. Instead, it follows the straightest possible path through space-time, whose geometry has been distorted by the sun's enormous mass. This idea sounded almost impossibly abstract. Fortunately, nature provided ways to test it. One of the earliest confirmations came from a curious detail in Mercury's orbit. Astronomers had long known that Mercury's closest approach to the sun slowly shifted over time. Most of this motion could be explained by the gravitational influence of the other planets. Yet a tiny residual discrepancy remained. It amounted to only 43 arcseconds per century, an angle so small that it is roughly comparable to the apparent width of a coin viewed from several kilometers away. Newton's theory could not account for it. General relativity predicted it precisely. For many physicists, this was the first indication that Einstein's new description captured something profoundly real. An even more dramatic test arrived during a total solar eclipse in 1919. According to general relativity, light itself should follow the curvature of space-time. Although photons possess no rest mass, they still travel along the geometry created by massive objects. If this were true, then starlight passing close to the sun should bend slightly before reaching Earth. Normally, the sun's brilliant glare hides nearby stars, but during a total eclipse, the moon blocks the sun's light, allowing astronomers to photograph stars positioned close to its edge. An expedition led by Arthur Eddington measured the apparent positions of those stars during the eclipse and compared them with photographs taken when the sun occupied another part of the sky. The stars appeared slightly displaced. Their light had bent exactly as Einstein's theory predicted. The result became one of the most celebrated confirmations in the history of science. Today, we know that the original measurements were more difficult and less precise than newspaper headlines suggested, and later observations with far better instruments have confirmed the effect with much greater accuracy. The important point was not that one eclipse solved every question. It was that the bending of light proved to be a genuine property of nature. Suddenly, light itself had become a probe of space-time. As telescopes improved throughout the 20th century, astronomers began seeing this phenomenon across the cosmos. Entire galaxies acted as enormous gravitational lenses. Clusters of galaxies bent the light from even more distant galaxies behind them. Sometimes a single distant quasar appeared as multiple images because its light had travelled along several different paths through curved space-time. These cosmic lenses became more than beautiful curiosities. They allowed astronomers to map otherwise invisible matter. Much of the bending could not be explained by the visible stars and gas alone. Hidden mass, now known as dark matter, contributed much of the gravitational curvature. Once again, light was revealing something that could not be seen directly. The deeper scientists looked, the more light seemed to function as the universe's most faithful messenger. It carried information across billions of light years. It responded to gravity without possessing rest mass. It traced invisible structures. It revealed galaxies too distant to visit and black holes too dark to observe directly. Every improvement in astronomy depended upon understanding how light travelled through space-time. Yet another remarkable realization quietly emerged. Although gravity can change light's direction, stretch its wavelength into redder colours, or compress it toward bluer ones, it does not change light speed measured locally. A photon climbing away from a massive object loses energy. One falling inward gains energy. Its frequency changes, its wavelength changes, but every observer making a local measurement still finds light travelling at exactly c. This consistency is extraordinary. Space-time itself may bend. Time itself may flow at different rates. Distances themselves may change depending on gravity and motion. Yet the local speed of light remains unchanged. The constant survives every transformation. It is almost as though the universe protects it. This realization encouraged physicists to think differently. Perhaps the speed of light was not simply another property of nature. Perhaps it reflected one of the deepest symmetries built into reality itself. But symmetries often arise from underlying structures. A snowflake reflects the molecular arrangement of water. A crystal reflects the geometry of its atoms. The hexagonal cells of a honeycomb emerge from countless individual choices made by bees following simple rules. Could space-time itself possess an underlying structure that gives rise to its remarkable properties? Quantum physics was beginning to suggest that empty space might not be empty at all. The vacuum, once imagined as perfect nothingness, appeared increasingly active beneath its quiet surface. Invisible fields filled every point in the cosmos. Tiny fluctuations briefly emerged and vanished. Particles and antiparticles flickered into existence for unimaginably short intervals before disappearing again. This was no longer the smooth, featureless emptiness of classical physics. It was a restless quantum vacuum. And if empty space possesses its own physical properties, another possibility naturally arises. Perhaps the speed of light is not simply imposed upon the vacuum. Perhaps it emerges from the vacuum itself. That idea remained speculative, but it pointed toward a fascinating new direction. The mystery was no longer confined to light. It had become a mystery about space, time, and even emptiness. To understand why light travels at the speed it does, scientists might first have to answer a more fundamental question. What is the vacuum of the universe actually made of by this point in our journey? The mystery has quietly changed shape. We began with a simple question about light itself. We wondered why it moves at nearly 300,000 kilometers every second. Along the way, we discover that this speed is far more than the velocity of a familiar beam shining through space. It defines the relationship between space and time. It determines how information travels. It shapes gravity, astronomy, and every successful theory describing the large-scale universe. And yet, after more than a century of extraordinary progress, the central question remains: why this speed? Not why is light fast, not why does relativity work, but why does the universe possess this particular fundamental constant at all? It is tempting to assume that science must already know the answer. After all, modern physics can predict the behavior of light with astonishing precision: quantum electrodynamics. The theory describing how light and charged particles interact agrees with experiments to more than 10 decimal places in some cases. General relativity predicts the bending of starlight, the motion of planets, and the existence of gravitational waves with remarkable accuracy. These theories work. Their predictions have survived countless experimental tests. But there is an important distinction between describing a law and explaining its origin. Newton's law of gravity accurately described how masses attract one another, but it did not explain why gravity exists. Darwin's theory explains how species evolve, but not why life first emerged. Similarly, relativity tells us how the speed of light governs space-time. It does not explain why space-time possesses exactly that invariant speed. This distinction may seem subtle, yet it lies at the heart of modern theoretical physics. Scientists often speak of fundamental constants. These are numbers that appear to be woven into the laws of nature themselves. The speed of light is one. Another is the gravitational constant, which determines the strength of gravity. Another is Planck's constant, which governs the quantum world. There are also the masses of elementary particles and several dimensionless numbers, such as the fine structure constant, that determine how strongly light interacts with electrically charged matter. If any of these values were even slightly different, the universe might look profoundly unlike the one we inhabit. Stars might burn differently. Atoms might never form. Chemistry could become impossible. Galaxies might fail to emerge. Or the universe might expand in ways that prevent complex structures from ever developing. This realization has led some people to wonder whether these constants are somehow chosen. Science, however, approaches the question more cautiously. The measurements are real. The deeper reason for those values remains unknown. Among these constants, the speed of light occupies a particularly unusual position. Unlike the mass of an electron or the charge of a proton, the speed of light does not merely describe one kind of particle. It defines the maximum speed at which cause can influence effect. If the sun were somehow to disappear instantly, Earth would continue orbiting for just over 8 minutes before the change in gravity reached us. Likewise, sunlight would continue arriving during those same 8 minutes. In general relativity, changes in gravity propagate no faster than light itself. The same cosmic limit governs both. This is why physicists increasingly speak of c not simply as the speed of light, but as the invariant speed of space-time. Light happens to travel at that speed because photons have no rest mass. Gravitational waves also travel at essentially the same speed. Any massless particle, according to our best current theories, would do the same. This shift in language is important. The constant existed in Einstein's equations before anyone had discovered photons in the modern quantum sense. Its significance extends beyond light itself. It appears to be a property of reality. But this only sharpens the mystery. Where do the laws of reality come from? One possibility is that the question simply has no deeper answer. Perhaps some constants are fundamental in the truest sense. They are not derived from anything else. They simply exist. This position is scientifically respectable because physics must eventually begin somewhere. Every theory rests upon assumptions. If one continually asks, what explains that? There may eventually come a point where no deeper explanation exists. Many physicists are comfortable with this possibility. Others are not. History offers a reason for their hesitation. Again and again, quantities once believed fundamental later turned out to emerge from deeper principles. Ancient astronomers regarded Earth's surface as fixed and immovable. Later, it became one planet among many. 19th century physicists regarded electricity and magnetism as separate forces. Maxwell revealed them as different aspects of one electromagnetic field. Even space and time, once considered completely independent, were united by Einstein into space-time. Each generation has discovered that what seemed fundamental often concealed a deeper layer. This historical pattern encourages physicists to keep asking questions. Could the speed of light also emerge from something beneath it? Several clues suggest that the search is worthwhile. One comes from the remarkable simplicity of Maxwell's equations. The speed of electromagnetic waves depends on two measurable properties of empty space. One describes how electric fields behave in the vacuum. The other describes how magnetic fields behave when these quantities are combined mathematically. The result is precisely the speed of light. This relationship is elegant. It tells us that the vacuum is not merely empty. It possesses measurable electromagnetic properties. But now another question appears. Why do those properties have exactly those values? The mystery has simply moved one step deeper. Instead of asking why light travels at c, we ask why the vacuum has the characteristics that produce c. Quantum physics complicates the story even further. According to quantum field theory, every point in space is permeated by invisible fields. Electrons arise as excitations of the electron field. Photons arise as excitations of the electromagnetic field. Quarks, neutrinos, and every known elementary particle are associated with their own quantum fields. The vacuum is therefore not empty. It is the lowest energy state of all these fields. Even in complete darkness, with every particle removed, these fields continue to exist. They fluctuate continuously because of quantum uncertainty. This has been confirmed indirectly through several measurable effects, including the Casimir effect and tiny shifts in atomic energy levels. The vacuum behaves like a physical system. If the vacuum has physical properties, then perhaps the speed of light reflects those properties. Some theoretical physicists have explored this possibility for decades. Could space-time resemble a material whose large-scale behavior emerges from microscopic structure? Just as sound travels through air because of countless molecular interactions, could light's invariant speed arise from some deeper architecture that becomes invisible at ordinary scales? At present, no experimental evidence confirms such an underlying structure. General relativity treats space-time as smooth. Quantum field theory successfully operates within that smooth space-time. But when physicists attempt to combine quantum mechanics with gravity, mathematical difficulties appear. The smooth picture begins to break down at extremely small distances, around the Planck length, approximately 1.66 to 10^35 meters, at such unimaginably tiny scales. Many researchers suspect that our current descriptions become incomplete. Perhaps space-time is not infinitely continuous. Perhaps it possesses a quantum structure. Perhaps the constant we call c emerges naturally from that deeper reality. Or perhaps not. This distinction is essential. The idea is scientifically motivated because existing theories become incomplete at the Planck scale. It is not an established fact. Different approaches to quantum gravity propose very different underlying pictures. Some preserve the constancy of C exactly. Others investigate whether subtle departures might occur under extreme conditions. So far, every observation has supported Einstein's prediction with extraordinary precision. Nature continues to protect this remarkable constant. The mystery therefore stands in a fascinating position. We know more about light than any previous generation in history. We know how it behaves inside atoms. We know how it crosses billions of light years. We know how gravity bends it. We know how quantum mechanics describes its interactions. Yet when we ask why the universe contains exactly this invariant speed, science reaches a quiet boundary. Beyond that boundary lie ideas, hypotheses, and ongoing research. The evidence has carried us remarkably far. To go farther, we must follow the evidence itself, examining what the universe actually allows us to observe, and what those observations can truly tell us about one of nature's most profound constants. When scientists encounter a mystery as deep as the origin of a fundamental constant, there is a natural temptation to search for an elegant explanation first. Science, however, has learned a different habit. Before proposing answers, it asks a simpler question. What can we actually observe? The distinction is essential. Observations are measurements made directly through experiments or instruments. From those observations, scientists construct models that explain the measurements. The models may become extraordinarily successful, but they remain separate from the evidence itself. This careful separation has guided astronomy for centuries. No one has ever held a star in their hand. No one has visited a distant galaxy. Everything we know about the universe beyond Earth has reached us in one form or another through light. If we hope to understand why light travels at the speed it does, the first step is to examine what light consistently tells us about itself. One of the most remarkable discoveries in all of science is not that light travels quickly. It is that every careful observation has found it to behave with extraordinary consistency. Whether photons leave the surface of the sun, the heart of a distant quasar, or a laser inside a laboratory, they obey the same fundamental rules. The environments could hardly be more different. Inside the sun's core, temperatures exceed 15 million degrees Celsius. Atomic nuclei collide with such tremendous energy that hydrogen fuses into helium, releasing photons that may spend hundreds of thousands of years slowly scattering outward or finally escaping into space. A laser operating on Earth is almost the opposite. Its photons are produced under carefully controlled laboratory conditions, emerging in highly organized waves with precisely defined frequencies. Yet once both sets of photons enter the vacuum of space, they travel according to exactly the same fundamental constant. The universe appears not to care where the light originated, only the conditions through which it travels. This remarkable universality extends across the entire electromagnetic spectrum. Visible light represents only a tiny fraction of electromagnetic radiation. Our eyes evolved to detect wavelengths useful beneath Earth's atmosphere, but nature is under no obligation to limit itself to human vision. Radio waves may stretch for kilometers. Microwaves are shorter. Infrared radiation carries heat. Visible light occupies only a narrow band. Beyond it lie ultraviolet light, X-rays, and gamma rays with wavelengths smaller than atoms. These forms of radiation differ enormously in energy. A radio photon carries vastly less energy than a gamma ray photon. Their frequencies differ by many orders of magnitude. Yet in a vacuum, every one of them travels at exactly the same speed. This simple fact is surprisingly profound. If the speed of light depended upon energy, astronomers would have noticed long ago. A distant supernova releases radiation across much of the electromagnetic spectrum. If higher energy photons travelled even slightly faster than lower energy photons through empty space, their arrival times would gradually separate over millions or billions of years. Instead, observations repeatedly show that after accounting for how the explosion itself unfolds, photons of different energies propagate through space in ways consistent with the same invariant speed. This has become one of the most powerful tests of modern physics. The universe itself serves as an enormous laboratory. Some of its experiments last billions of years. One particularly valuable source of evidence comes from pulsars. Pulsars are rapidly rotating neutron stars. the incredibly dense remnants left behind after massive stars explode as supernovae, although only about 20 kilometers across. A neutron star may contain more mass than the Sun. Its magnetic field channels intense beams of electromagnetic radiation outward from its magnetic poles. As the star rotates, these beams sweep across space like the light from a distant lighthouse. Whenever one crosses Earth, telescopes detect a pulse. Some pulsars rotate hundreds of times each second. Their pulses arrive with astonishing regularity. The timing is so precise that certain pulses rival the stability of atomic clocks. This precision makes them extraordinary laboratories for testing relativity. If the speed of light varied unpredictably across space, the pulses arriving from distant neutron stars would gradually lose their remarkable regularity. Instead, astronomers observe consistency so extraordinary that tiny deviations become valuable tools for studying gravitational waves and the motion of our own solar system. Light continues to behave exactly as Einstein's theory predicts. Another line of evidence comes from gravitational lensing. Earlier we saw that massive galaxies bend light by curving space-time. Sometimes astronomers observe multiple images of the same distant quasar because light has travelled along several different routes around an intervening galaxy. Each path has a slightly different length. Each also passes through regions where gravity affects the flow of time differently. As a result, the images do not all arrive simultaneously. One image may appear days or even weeks before another. These measurable delays agree remarkably well with calculations based on general relativity. Once again, the observations are not merely confirming that gravity bends light. They are confirming that light continues to obey the same fundamental geometric rules while crossing billions of light-years of curved space-time. Perhaps the most dramatic evidence arrived only recently. For decades, gravitational waves remained one of Einstein's boldest predictions. According to general relativity, accelerating massive objects should generate ripples in space-time itself. These waves travel outward, carrying energy across the cosmos. Detecting them required measuring changes in distance smaller than the width of an atomic nucleus over arms 4 kilometers long. In 2015, the Laser Interferometer Gravitational Wave Observatory, better known as LIGO, achieved that remarkable feat. The signal came from two merging black holes more than 1 billion light-years away. Later detections revealed collisions involving neutron stars. One event, observed in 2017, proved especially important. Astronomers detected gravitational waves from two merging neutron stars. Within seconds, telescopes around the world observed light from the same event. For the first time, humanity witnessed both forms of cosmic messenger arriving from a single astrophysical catastrophe. The result carried enormous significance. The difference between the arrival times of the gravitational waves and the light was entirely consistent with the physical processes occurring during the merger itself. Not with any significant difference in propagation speed across the immense distance they had travelled. After crossing roughly 130 million light-years of space, gravitational waves and light reached Earth travelling at essentially the same cosmic speed. If there had been even a tiny discrepancy in their fundamental propagation through space-time, this journey would almost certainly have revealed it. Instead, Einstein's prediction survived another remarkable test. Astronomers also study the oldest light in existence. The cosmic microwave background began its journey approximately 380,000 years after the Big Bang, when the expanding universe cooled enough for electrons and atomic nuclei to combine into neutral atoms. Before that moment, the young universe was an opaque plasma. Photons scattered constantly from charged particles. As soon as neutral atoms formed, light could finally travel freely. Those ancient photons have been crossing space for nearly 13.8 billion years. Today they fill the entire sky as faint microwave radiation. Spacecraft such as COBE, WMAP, and Planck have mapped this relic light with extraordinary precision. Tiny variations in its temperature reveal the seeds from which galaxies later formed. More importantly for our story, these observations agree with a universe in which light has propagated according to the same fundamental laws throughout nearly all of cosmic history. That conclusion carries enormous weight. It does not prove that the speed of light has always possessed exactly the same value under every conceivable circumstance. Science is careful not to claim more than the evidence allows. What it does show is that across an immense range of environments, distances, and epochs. Every observation remains consistent with a remarkably stable invariant speed. This distinction matters. Scientists rarely claim absolute certainty. Instead, they ask whether observations require changing an existing theory. So far, they do not. Many theoretical proposals have explored whether the speed of light might vary under extreme conditions, perhaps near the beginning of the universe or at energies approaching the Planck scale. These ideas remain active areas of research, yet every astronomical observation capable of testing them has imposed increasingly stringent limits. Nature continues to resist even the smallest detectable deviation. Piece by piece, the evidence has built an extraordinary picture: light from atoms, light from pulsars, light bent by galaxies, light accompanying gravitational waves, light left over from the birth of the cosmos. Each observation tells a remarkably consistent story, not because scientists insist that it must, because the universe itself continues to tell that story every time we listen. And yet consistency is not the same as explanation. The observations reveal what light does. They do not tell us why reality is organized this way. To answer that deeper question, physicists have developed several competing ideas, each attempting to explain why the universe possesses this extraordinary constant while remaining faithful to everything the evidence has revealed. When evidence reaches the limits of what it can directly reveal, science enters a quieter phase. This is where theories become essential. A scientific theory is not a guess. It is a carefully constructed framework that attempts to explain observations while making predictions that can, in principle, be tested. Some theories survive repeated challenges and become deeply established. Others remain promising but incomplete. Still others eventually give way to better explanations. The question before us belongs to this frontier. Why does the universe possess an invariant speed? No experiment has yet provided a definitive answer. Instead, physicists have developed several ways of thinking about the problem. Each begins with the same observations. Each respects the extraordinary success of relativity. Yet each places the origin of the speed of light in a different part of nature's architecture. To understand the current scientific landscape, it is helpful to separate what is firmly established from what remains uncertain. The observed fact is straightforward. Light travels through a vacuum at the same invariant speed for every local observer. Gravitational waves propagate at essentially the same speed. Every successful experiment performed so far agrees with this picture. The accepted theory explaining these observations is Einstein's relativity. Special relativity describes how measurements of space and time change for observers in relative motion. General relativity extends those ideas to gravity, describing it as the curvature of space-time. Together, these theories have passed more than a century of increasingly precise experimental tests. What relativity does not attempt to explain is why space-time possesses this invariant speed in the first place. That deeper question is where competing ideas begin. The first possibility is, in many ways, the simplest. Perhaps the speed of light is genuinely fundamental. In this view, there is no hidden mechanism waiting to be discovered. The constant c is simply one of the basic ingredients from which the laws of physics are built. Just as geometry begins with certain axioms, perhaps nature begins with a handful of constants that cannot be derived from anything deeper. Many physicists consider this possibility entirely reasonable. After all, every scientific theory must begin somewhere. If one continually asks what explains each explanation, the chain cannot continue forever. Eventually, one may arrive at principles that simply define reality itself. The strength of this idea is its simplicity. It requires no additional assumptions. It is fully compatible with every successful experiment. Its limitation is equally clear. It does not satisfy those who hope that apparently fundamental constants might eventually emerge from deeper laws. History has repeatedly shown that seemingly independent facts can often be unified. Many researchers therefore continue searching. A second perspective begins with quantum field theory. According to this framework, every elementary particle corresponds to an underlying quantum field extending throughout all of space. The electromagnetic field gives rise to photons. The electron field gives rise to electrons. Other fields produce quarks, neutrinos, and the particles responsible for the weak and strong nuclear forces. Within this picture, the vacuum is not empty. It is the lowest energy configuration of all these fields. Virtual fluctuations continually appear and disappear. Although these are not particles in the ordinary sense, but mathematical features of quantum fields whose effects can sometimes be measured indirectly. Some physicists ask whether the invariant speed arises naturally from the relationships among these fields. Perhaps C reflects the symmetry of the quantum vacuum itself. This idea is attractive because symmetry plays a profound role throughout modern physics. Whenever nature exhibits a deep symmetry, important conservation laws often follow. The symmetry underlying relativity, known as Lorentz symmetry, ensures that the laws of physics remain the same for observers moving uniformly relative to one another. The invariant speed appears naturally within this symmetry. Yet another question immediately follows. Why does Lorentz symmetry exist? Again, the explanation seems to move one level deeper rather than ending. A third family of ideas emerges from attempts to unite quantum mechanics with gravity. General relativity treats space-time as smooth and continuous. Quantum mechanics describes a world where many physical quantities become quantized. Reconciling these two extraordinarily successful theories has proven one of the greatest challenges in modern physics. Several approaches have been developed. One is known as loop quantum gravity. In simplified terms, it suggests that space-time itself may possess a discrete microscopic structure, rather than being infinitely divisible. Instead of a perfectly smooth fabric, space-time might resemble an intricate network at scales far beyond direct observation. Importantly, current versions of loop quantum gravity are generally constructed to recover Einstein's relativity at ordinary scales. The invariant speed of light remains an essential feature of the large-scale universe. Whether it ultimately emerges from the microscopic structure or remains fundamental within that structure is still an open question. Another major research program is string theory. In this framework, elementary particles are not point-like objects, but tiny vibrating strings existing within additional mathematical dimensions. Different vibration patterns correspond to different particles. String theory naturally incorporates gravity and offers one possible route toward a unified description of all known forces. Within the theory, the familiar speed of light continues to arise through the geometry and symmetries of space-time. However, despite decades of mathematical development, string theory has not yet produced experimental evidence distinguishing it from competing approaches. Its mathematical richness is undeniable. Its status as a physical description of nature remains under active investigation. A different class of hypotheses asks a more radical question. Could the speed of light itself vary under certain extreme conditions? This idea is known broadly as varying speed of light cosmology. It should be approached carefully. These proposals do not suggest that scientists have observed the speed of light changing in laboratories today. Instead, some models explore whether, during the extraordinarily hot and dense conditions shortly after the Big Bang, the effective propagation speed associated with light or space-time might have differed from its present value. The motivation is not to replace relativity casually. Rather, these models attempt to address certain puzzles in cosmology, such as why distant regions of the universe appear so similar despite their enormous separation. Some versions offer alternatives to aspects of cosmic inflation, while others are compatible with inflationary ideas. At present, observation strongly constrains such models. No compelling evidence has established that the invariant speed measured today has changed during the observable history of the universe. For that reason, these ideas remain hypotheses rather than accepted theories. There is another intriguing perspective that has gained attention in recent decades. Some physicists have begun exploring whether space-time itself could be an emergent phenomenon. This idea turns our intuition upside down. Instead of treating space-time as the fundamental stage upon which everything happens, perhaps space-time arises from something even deeper. An analogy can help, provided we remember that it is only an analogy. Temperature feels like a basic property of matter, yet a single molecule has no temperature. Temperature emerges only from the collective motion of enormous numbers of molecules. Likewise, the smooth flow of water emerges from countless individual atoms. Could space-time emerge from microscopic degrees of freedom that we have not yet identified? If so, perhaps the invariant speed of light would emerge naturally as one of the large-scale properties of that deeper system. This possibility appears in several modern research directions, including approaches involving quantum information, holographic principles, and condensed matter analogies. These fields are mathematically sophisticated and remain highly active areas of investigation. What they share is not a common answer. It is a common question. Could the geometry of space-time itself be a consequence rather than a starting point? At present, no experimental evidence allows scientists to choose decisively among these deeper possibilities. That uncertainty is important. Science progresses by comparing predictions with observation. A beautiful mathematical framework is not enough. Nature has the final word. For now, Einstein's description continues to agree with every precision test. Any successful future theory must therefore reproduce relativity where relativity has already proven correct. It must explain not only why the speed of light is invariant, but also why every experiment has found it to be so with astonishing precision. This requirement is extraordinarily demanding. Many elegant ideas have failed because they predicted effects that careful observations never revealed. Others remain viable precisely because current technology cannot yet distinguish them. So where does this leave us? We have established the facts. We have followed the evidence. We have explored the principal theoretical landscapes. None has yet provided a universally accepted explanation for why the invariant speed possesses its specific value. Yet one possibility stands out because of its profound implications. Suppose, for a moment, that the speed of light is not an arbitrary number written into the laws of physics. Suppose instead that it is a natural consequence of a deeper structure from which space, time, and perhaps even gravity themselves emerge. If that idea were true, what kind of universe would we expect to see? That question leads us from competing explanations toward one carefully grounded thought experiment, where established science gradually gives way to the frontier of theoretical possibility. Among the many ideas that physicists have explored, one is especially intriguing because it changes the direction of the question itself. Instead of asking why the speed of light has a particular value, it asks whether that value is something the universe must possess once deeper laws are taken into account. This is not an accepted scientific conclusion. It is a carefully motivated possibility, one that appears in several branches of modern theoretical physics. Exploring it requires a different way of thinking. Throughout history, science has repeatedly discovered that many familiar properties of nature are not fundamental after all. Consider the behavior of sound. To everyday experience, sound seems like an independent phenomenon. A bell rings, thunder echoes across the sky, music fills a concert hall. Yet sound is not a basic ingredient of the universe. It emerges from countless microscopic interactions between atoms and molecules. The speed of sound is therefore not an arbitrary number. It depends on the properties of the material through which it travels. In air at room temperature, it moves at roughly 343 meters per second. In water, it travels more than 4 times faster. In steel, faster still. Change the underlying material, and the emergent speed changes naturally. No single molecule contains the speed of sound. It appears only when enormous numbers of molecules behave collectively. This distinction between fundamental and emergent behavior appears throughout physics. Temperature is another example. A single atom does not possess a temperature. Only a collection of many particles moving statistically can be described as hot or cold. Pressure, viscosity, elasticity, and fluid turbulence all emerge from deeper microscopic interactions. The large-scale world often possesses properties that cannot be assigned to its smallest components individually. This raises an intriguing possibility. Could space-time itself be similar? General relativity describes space-time as a smooth geometric fabric. But perhaps smoothness is only an approximation. Perhaps, at unimaginably small scales, reality consists of something far more fundamental. If so, then space-time might resemble the surface of a calm ocean. From a great height, the ocean appears continuous. Its waves flow gracefully across the horizon. Yet close inspection reveals countless individual water molecules. The apparent smoothness is an emergent illusion created by enormous numbers of microscopic constituents. Several modern research programs investigate whether space-time behaves in a comparable way. They differ substantially in their mathematics and physical assumptions, but many share a common philosophical direction. The geometry we experience may not be the deepest level of reality. Instead, geometry itself may emerge. If that were true, the invariant speed represented by c might emerge as well, not because nature arbitrarily selected one number among infinitely many, but because the deeper structure naturally produces that value, in the same way crystalline solids naturally produce particular elastic properties. At this point, it is essential to distinguish carefully between established science and theoretical exploration. The idea that space-time could be emergent is an active area of research. The conclusion that this explains the speed of light has not been demonstrated. The evidence neither confirms nor rules it out. It remains a scientifically motivated possibility. Still, it is worth asking what consequences would follow if such an idea proved correct. One immediate consequence would concern the meaning of empty space. For centuries, physicists gradually abandoned the notion that the vacuum is simple nothingness. Quantum field theory already tells us that every point in space contains quantum fields. Virtual fluctuations continuously contribute to measurable physical effects. Even the lowest energy state of the vacuum possesses structure. If space-time itself also emerges from something deeper, then the vacuum would represent far more than empty geometry. It would become an organized physical system. The smooth arena in which particles move would itself be the collective behavior of an underlying microscopic reality. In that case, photons would not merely cross space. They would propagate through an emergent space-time whose large-scale properties naturally define the invariant speed. Notice how different this idea is from the old ether. The 19th century ether was imagined as a material filling otherwise classical space. Modern emergent space-time proposals do not restore that picture. Instead, they question whether classical space-time exists fundamentally at all. The distinction is profound. The ether assumed that space already existed. Emergent theories ask whether space itself is the phenomenon requiring explanation. Another implication concerns causality. Today, the speed of light defines the maximum rate at which information can propagate. This limitation preserves the causal order of events. Effects cannot outrun their causes. The structure of space-time itself guarantees this relationship. If space-time emerges from deeper principles, then causality might also emerge from those same principles. Rather than being imposed from above, the familiar causal structure of the universe could arise naturally from the microscopic organization of reality. Some researchers find this possibility especially attractive because it hints at a common origin for several seemingly independent features of physics: geometry, information, entropy, quantum entanglement, the invariant speed. Instead of treating these as unrelated ingredients, perhaps they are different expressions of one deeper framework. Hints of this possibility appear in several modern ideas. The holographic principle, inspired partly by the thermodynamics of black holes, suggests that the information describing a volume of space may be encoded on its boundary. Although originally developed in a specific theoretical context, it has profoundly influenced thinking about quantum gravity. Meanwhile, studies of quantum information have revealed surprising mathematical relationships between entanglement and the geometry of space-time in certain theoretical models. These developments do not prove that space-time literally emerges from entanglement. They do suggest that concepts once thought completely separate may be more closely connected than previously imagined. This growing web of connections is one reason the idea continues to receive serious attention. Yet every thoughtful scientist must also acknowledge its limitations. At present, no experiment has directly observed the microscopic structure from which space-time would emerge. No telescope has photographed it. No particle accelerator has reached the energies where such structure might become unmistakable. The Planck scale remains unimaginably remote from current technology. Its characteristic length, around 10-35 meters, is roughly 20 orders of magnitude smaller than the diameter of a proton. Bridging that gulf is among the greatest experimental challenges in all of science. Consequently, many different theoretical pictures remain compatible with today's observations. Some predict that Lorentz symmetry remains exact at every scale. Others allow incredibly tiny departures that might accumulate across billions of light years. Astronomers have searched carefully for such effects. High-energy photons from distant gamma-ray bursts provide one opportunity. If space-time possessed certain kinds of microscopic structure, photons of different energies might accumulate minute differences in travel time over cosmic distances. Observatories have looked for precisely this signature. So far, the results have imposed increasingly strict limits. No convincing evidence for such energy-dependent propagation has emerged. Again, nature appears remarkably faithful to Einstein's picture. Far from discouraging researchers, this strengthens the challenge. Any deeper theory must explain not only why space-time behaves as relativity predicts at familiar scales, but why those predictions remain so extraordinarily accurate across the observable universe. That is no small requirement. If space-time truly emerges, it does so with astonishing elegance. As our thought experiment draws to a close, one realization becomes difficult to ignore. Whether the invariant speed is fundamental or emergent, its influence extends far beyond light itself. It shapes the birth of stars, the collapse of black holes, the expansion of the cosmos, the formation of galaxies, the very history of the observable universe. To understand why one number appears throughout so many different corners of physics, we must now step back and view the entire cosmic landscape. Only then can we appreciate just how deeply the speed of light is woven into the architecture of existence. By now, the speed of light has become something very different from the familiar number introduced at the beginning of our journey. It is no longer simply the rate at which sunlight reaches Earth, or the velocity recorded in a laboratory experiment. Instead, it has gradually revealed itself as one of the organizing principles of the cosmos, quietly shaping events from the smallest scales of quantum physics to the largest structures ever observed. To appreciate how deeply this single constant influences the universe, we must step outward, not by a few kilometers, not even by a few light years, but across the entire history of cosmic evolution. The story begins only fractions of a second after the Big Bang. Our current understanding describes the early universe as extraordinarily hot and dense. Temperatures were so immense that familiar atoms could not exist. Even atomic nuclei had not yet formed. Matter and radiation existed in a rapidly expanding sea of elementary particles interacting continuously with one another. During these earliest moments, light could not travel freely. Photons certainly existed, but they were constantly scattered by electrically charged particles. Every attempt to move through space was interrupted almost immediately by another interaction. The young universe resembled a dense fog. In a thick earthly fog, light still travels locally at its normal speed between collisions, but repeated scattering prevents it from moving freely over long distances. The early universe behaved in a broadly similar way. Only after approximately 380,000 years of expansion did temperatures fall enough for electrons to combine with nuclei and form neutral atoms. This event is known as recombination. Suddenly the fog cleared. Photons were no longer scattered incessantly. For the first time, light could travel enormous distances almost uninterrupted. Those ancient photons still exist today. We detect them as the cosmic microwave background. In a very real sense, the oldest observable light in the universe marks the moment when the cosmos first became transparent. Without the invariant speed of light, this transition would have unfolded differently. Indeed, nearly every stage of cosmic evolution would. The expansion of the universe itself is intimately connected to this constant. One subtle point often causes confusion. Astronomers sometimes observe distant galaxies whose separation from us increases faster than the speed of light because space itself expands. This does not violate relativity. Relativity limits how quickly objects and information move through space-time. It does not impose the same restriction on the expansion of space-time itself. An analogy can help, provided we remember its limits. Imagine drawing two dots on the surface of an inflating balloon. The dots need not move across the rubber at all. Instead, the rubber stretches between them. Their separation increases because the surface expands. Likewise, galaxies carried by cosmic expansion are largely following the evolution of space-time itself rather than racing through space like spacecraft. This distinction preserves one of relativity's deepest principles. No signal carrying information outruns the invariant speed locally. The geometry of the universe may evolve. Its local causal structure remains intact. The same constant governs the life cycles of stars. Deep within stellar cores, nuclear fusion converts small amounts of mass into enormous quantities of energy. Einstein's famous relationship, E=mc captures this connection. Although often remembered as an elegant equation, its consequences are astonishingly practical. The factor C2 is enormous because the speed of light is such a large number. Squaring it produces an even larger conversion factor between mass and energy. This is why tiny reductions in mass during fusion can power stars for billions of years. Every sunrise on Earth ultimately depends upon this relationship. Hydrogen nuclei merge into helium. A small amount of mass disappears. Its energy emerges as photons that slowly work their way outward through the sun before beginning their 8-minute journey toward our planet. The same principle governs far more dramatic events. When massive stars exhaust their nuclear fuel, gravity overwhelms the outward pressure generated by fusion. The stellar core collapses. Depending upon its mass, the result may become a neutron star or a black hole. Throughout these violent transformations, the invariant speed continues to define how information propagates. Shock waves, neutrinos, photons, gravitational waves. Each obeys the causal structure established by space-time. Even black holes reveal how deeply this constant is embedded within reality. The defining boundary of a black hole, the event horizon, is often misunderstood. It is not a solid surface. Instead, it marks the region from which no future-directed path leading outward exists for light itself, because nothing carrying information can exceed the invariant speed. Anything crossing the event horizon can no longer communicate with the outside universe. This is not because gravity somehow accelerates inward faster than light. It is because space-time has become curved so severely that every future path available to light points deeper toward the black hole's interior. The geometry itself has changed. Again, the speed of light quietly defines the structure of possibility. Galaxies provide another perspective. The Milky Way stretches roughly 100,000 light-years across. If a civilization lived on opposite sides of our galaxy, even messages traveling at the speed of light would require 100,000 years to cross from one side to the other. The galaxy therefore cannot behave like a perfectly connected system. Communication itself unfolds gradually, because spreads through the galaxy only as rapidly as the invariant speed allows. At still larger scales, clusters of galaxies assemble through gravity over billions of years. Dark matter forms immense invisible scaffolds along which ordinary matter accumulates. Filaments hundreds of millions of light-years long connect galaxy clusters into what astronomers call the cosmic web. Every stage of this growth depends upon signals propagating through space-time at finite speed. Gravity cannot reorganize the universe instantaneously. Information about changing mass distribution spreads outward causally. The cosmos evolves patiently. One region influences another only after sufficient time has passed. This finite speed has profound philosophical consequences as well. There is no universal now. When we observe a galaxy 10 billion light-years away, we are not seeing it as it exists today. We are seeing it as it existed when its light began the journey toward Earth. Different parts of the observable universe are always observed at different moments in their histories. Astronomy therefore resembles archaeology on the grandest conceivable scale. Each additional distance is also an additional journey into the past. The farther telescopes see, the younger the universe becomes. This remarkable feature would disappear if information propagated instantaneously. History itself would become observationally inaccessible. Instead, the finite speed of light preserves the chronological richness of the cosmos. It allows astronomers to reconstruct cosmic evolution directly rather than merely infer it. Even the largest computer simulations of cosmic structure rely fundamentally upon this constant. Programs modeling galaxy formation must account for radiation traveling through gas, stellar explosions influencing surrounding regions, black holes emitting energetic jets, and gravity reshaping space-time. Although simulations often simplify certain physical processes for computational practicality, the causal framework established by relativity remains indispensable. Without it, the simulated universe would no longer resemble the observed one. Perhaps most remarkably, this same constant links together branches of physics that once appeared unrelated. It connects electromagnetism through Maxwell's equations, relativity through Einstein's geometry, quantum theory through photons, astrophysics through stellar evolution, cosmology through the expansion of the universe, particle physics through mass-energy equivalence. Few numbers in science possess such extraordinary reach. Yet despite its central role, the origin of this invariant speed remains elusive. We understand with increasing confidence what it does. We understand how to incorporate it into every successful physical theory. But why reality itself possesses precisely this structure remains unanswered. As researchers explored ever more specialized areas of physics during the 20th and 21st centuries, something unexpected began to happen. Ideas that once seemed completely independent started converging. Black holes began teaching lessons about information. Quantum entanglement began illuminating geometry. Thermodynamics began appearing inside gravity. Concepts developed in one discipline unexpectedly resurfaced in another. It was as though distant branches of physics were quietly pointing toward the same hidden foundation. And somewhere near that unseen foundation, the mystery of the speed of light continued to wait. One of the most satisfying moments in science occurs when ideas that once seemed completely unrelated suddenly begin to fit together. Not because anyone forced them to, not because a single equation magically explains everything, but because observations gathered over decades, sometimes centuries, begin revealing patterns that were invisible when each discovery stood alone. The story of the speed of light has reached that stage. For much of scientific history, electricity belonged to one field. Gravity belonged to another. Heat seemed entirely separate. The behavior of atoms occupied its own corner of physics. Astronomy appeared to concern distant objects rather than the laws governing everyday life. Today, those boundaries have become remarkably porous. Again and again, researchers have found that the same fundamental principles quietly reappear across these different domains. The invariant speed of light is one of the strongest threads connecting them. One of the most surprising connections involves information. At first glance, information sounds like a concept borrowed from communication technology or computer science. A message travels through a cable. A photograph is stored on a hard drive. A radio signal crosses the atmosphere. Yet modern physics treats information much more broadly. Whenever one physical system influences another, information has been transferred. A photon striking your retina carries information about a distant star. A gravitational wave passing through Earth carries information about two black holes that collided more than 1 billion years ago. Even the arrangement of atoms inside a crystal contains information about how the crystal formed. In every known case, that information propagates according to the same causal structure established by relativity. Nothing carrying usable information has ever been observed traveling faster than the invariant speed. This fact is so deeply embedded in modern physics that many researchers now regard c less as the speed of light than as the speed of causality itself. Light merely happens to travel at that limit because photons have no rest mass. The connection becomes even richer when we turn to entropy. Entropy is often described as a measure of disorder, although many physicists prefer to think of it as a measure of how many microscopic arrangements correspond to the same large-scale state. A shuffled deck of cards can exist in vastly more arrangements than one perfectly ordered by suit. A gas filling a container has enormously more possible microscopic configurations than gas compressed into one corner. Entropy therefore tends to increase because high-entropy states are statistically far more numerous. This simple idea unexpectedly entered gravitational physics through black holes. For decades, black holes appeared strangely simple. According to classical general relativity, they could be described almost entirely by their mass, electric charge, and angular momentum. Everything else seemed to disappear behind the event horizon. Then, during the early 1970s, a remarkable insight emerged. The physicist Jacob Bekenstein proposed that black holes should possess entropy. Initially, the suggestion seemed almost impossible. Entropy normally counts microscopic internal states, but if nothing escapes a black hole, what microscopic states could possibly be counted? Soon afterward, Stephen Hawking combined quantum field theory with curved space-time and discovered something even more surprising. Black holes are not perfectly black. Quantum effects near the event horizon allow them to emit an extremely faint thermal radiation, now known as Hawking radiation. This prediction transformed black holes from completely silent objects into thermodynamic systems possessing temperature and entropy. The details remain an active area of research because a complete quantum theory of gravity has not yet been achieved. Nevertheless, one extraordinary feature became immediately apparent. The entropy of a black hole is proportional not to its volume, but but to the area of its event horizon. That relationship was profoundly unexpected. Ordinary physical systems generally scale with volume. Black holes appear to obey a different rule. This observation inspired later developments that eventually contributed to the holographic principle. The principle, in its broadest conceptual form, suggests that the information describing a region of space may sometimes be represented on its boundary. The precise mathematical realization depends on the theoretical framework being considered, and physicists continue investigating how broadly the idea applies. Still, its implications have been enormously influential. Once again, geometry and information began appearing together. The connection did not stop there. Quantum mechanics introduced another remarkable phenomenon: entanglement. When two particles become entangled, measurements performed on one are statistically correlated with measurements performed on the other, even after they are separated by vast distances. This does not allow faster-than-light communication. That point is crucial. Although the correlations are real, they cannot be used to transmit usable information instantaneously. Relativity remains intact, yet entanglement reveals that quantum systems can possess relationships extending beyond classical intuition. Over the past 2 decades, researchers studying quantum gravity have uncovered increasingly deep mathematical connections between entanglement and space-time geometry in certain theoretical models. In some formulations, changing patterns of entanglement correspond to changes in geometric structure. This has led to a provocative question. Could space-time itself be intimately related to the organization of quantum information? It is important not to overstate this idea. No experiment has yet demonstrated that space-time literally emerges from entanglement. Current work explores mathematically precise relationships within specific theoretical settings. These developments are exciting because they reveal unexpected unity, not because they have settled the question. The distinction matters. Scientific frontiers are often surrounded by enthusiastic speculation. Careful researchers continually distinguish what the mathematics demonstrates from what remains interpretive. Another unexpected bridge links gravity and thermodynamics. In everyday life, heat flows naturally from warmer objects toward cooler ones. This familiar behavior reflects statistical laws governing enormous numbers of microscopic particles. Remarkably, several researchers have shown that equations closely resembling Einstein's gravitational field equations can be derived using thermodynamic reasoning under certain assumptions. Among the pioneers of this approach was Ted Jacobson, who demonstrated that aspects of general relativity can emerge from relationships involving entropy and energy flow across local horizons. This does not prove that gravity is simply thermodynamics. It does suggest that thermodynamic principles may lie much deeper within space-time than previously suspected. Again, a familiar pattern appears: geometry, entropy, information, causality. Each field begins independently. Each gradually converges. The speed of light quietly remains present throughout, without its invariant causal structure. These relationships would not fit together consistently. Even particle physics contributes to this growing web. Inside particle accelerators, collisions lasting less than a trillionth of a second produce showers of elementary particles. The calculations describing these events rely upon quantum field theory, whose equations fully respect Lorentz symmetry and the invariant speed. Meanwhile, astronomers studying neutron stars, quasars, and gravitational waves use relativity on cosmic scales. Remarkably, despite operating across more than 40 orders of magnitude in size, both descriptions continue employing the same fundamental causal limit. Few scientific principles display such extraordinary universality. Perhaps this is why so many physicists suspect there must be a deeper explanation. History repeatedly teaches that broad unification often hints at hidden simplicity. Electricity and magnetism became electromagnetism. Space and time became space-time. Mass and energy became interchangeable through relativity. Perhaps information, geometry, entropy, and quantum mechanics are also different faces of one deeper structure. If so, the invariant speed may not merely connect these ideas. It may arise from the very principle that unites them. For now, that possibility remains an active area of theoretical investigation rather than established knowledge. No experiment has yet revealed the underlying framework with certainty. Nevertheless, The growing convergence has changed the direction of modern research. Physicists are increasingly searching not for isolated explanations, but for principles capable of connecting many successful theories simultaneously. To pursue those principles, they have built instruments unlike anything previous generations could have imagined. Space telescopes capable of observing the earliest galaxies, interferometers measuring distortions smaller than atomic nuclei, particle accelerators recreating conditions fractions of a second after the Big Bang, radio arrays spanning continents, precision atomic clocks sensitive enough to detect tiny changes in gravity. Each instrument extends humanity's senses a little farther. Each offers another opportunity to ask whether the deepest constants of nature conceal an even deeper story. Every generation of astronomers inherits a remarkable advantage over the one before it. The universe itself does not change very quickly. The stars continue shining. Galaxies continue evolving. Light continues crossing the vast spaces between them. What changes are the instruments we use to observe them? A telescope that once revealed hundreds of stars is eventually replaced by one that reveals hundreds of millions. A detector that once measured seconds learns to measure billionths of a second. Each technological advance makes the cosmos appear both more familiar and more mysterious. This has been especially true during the past few decades. Modern astronomy has entered an era of extraordinary precision. Rather than asking whether Einstein's theories are broadly correct, researchers now search for deviations so small that they would have escaped every previous generation of experiments. If the speed of light is truly one of the deepest constants in nature, then every improvement in measurement provides another opportunity to test that assumption. One of the most powerful observatories in this effort never looks through a traditional eyepiece. It circles Earth quietly above the atmosphere. The European Space Agency's Gaia spacecraft has spent years measuring the positions and motions of nearly 2 billion stars within the Milky Way. Its measurements are so precise that it can detect apparent positional shifts comparable to observing a coin on the Moon from Earth. Although Gaia was designed primarily to map our galaxy, its data also provide increasingly stringent tests of gravity and relativity. Whenever light bends near massive objects or travels through slightly curved space-time, those tiny effects become part of the measurements. The remarkable agreement between observation and Einstein's predictions continues to strengthen confidence in the underlying framework. At the opposite end of the electromagnetic spectrum, radio astronomy has become an equally powerful laboratory. Very long baseline interferometry, commonly abbreviated VLBI, combines radio telescopes separated by thousands of kilometers into what is effectively one enormous Earth-sized instrument. Signals arriving at different observatories are synchronized using extraordinarily stable atomic clocks. By comparing the arrival times with exquisite precision, astronomers produce images of astonishing sharpness. This technique played a central role in creating the first images of the shadows cast by supermassive black holes. The Event Horizon Telescope, a global network of radio observatories, used this method to image the black hole at the center of the galaxy M87 and later the black hole at the center of our own Milky Way. Although the images are often described as photographs, they are sophisticated reconstructions based upon precisely timed radio signals. Their agreement with predictions from general relativity provides yet another confirmation that light behaves exactly as expected even within some of the strongest gravitational fields accessible to observation. Meanwhile, space telescopes have extended humanity's vision farther into cosmic history than ever before. The Hubble Space Telescope transformed astronomy by revealing galaxies whose light had traveled for billions of years before reaching Earth. More recently, the James Webb Space Telescope has pushed that frontier even closer to the dawn of galaxy formation. Its infrared instruments detect ancient light stretched to longer wavelengths by cosmic expansion. Each newly observed galaxy becomes another test of the laws governing light over enormous distances and times. So far, every observation remains consistent with the same invariant speed shaping the evolution of the observable universe. Modern cosmology also relies heavily on enormous astronomical surveys. Projects mapping millions of galaxies allow researchers to reconstruct the large-scale structure of the cosmos with unprecedented detail. Tiny statistical patterns reveal how matter clustered over billions of years. These maps constrain theories involving dark matter, dark energy, and gravity itself. If the propagation of light differed even subtly from Einstein's predictions across cosmological distances, such surveys might eventually reveal inconsistencies. Instead, they continue tightening the limits within which alternative theories must operate. Not all modern tests involve telescopes. Some occur beneath mountains or deep underground. Particle physics laboratories seek to understand the fundamental constituents of matter under controlled experimental conditions. The Large Hadron Collider accelerates protons to energies approaching those that existed fractions of a second after the Big Bang. When the protons collide, detectors record the resulting particle showers with extraordinary precision. These experiments do not measure the speed of light directly. Rather, they test the quantum field theories whose equations incorporate Lorentz symmetry, the same symmetry underlying the invariant speed. So far, those theories continue to perform with remarkable success. No experimentally confirmed violation of Lorentz symmetry has yet appeared. Another powerful avenue of investigation comes from atomic clocks. Today's best optical atomic clocks lose or gain less than a second over billions of years. Their precision has become so extraordinary that moving one clock upward by only a few centimeters changes the measured flow of time because of Earth's gravitational field. These clocks now serve not only as timekeepers, but also as laboratories for testing relativity itself, if hidden physical processes cause tiny variations in fundamental constants. Networks of ultra-precise clocks might eventually detect them. Researchers are actively exploring this possibility. The results thus far continue to support the remarkable stability of nature's fundamental laws. Gravitational wave astronomy has added an entirely new sense through which humanity observes the universe. Before 2015, astronomy relied almost exclusively on electromagnetic radiation. Now space-time itself has become an observable messenger. Each new gravitational wave detection provides another opportunity to compare the propagation of gravity with the propagation of light. The growing catalogue of events continues to reinforce one of relativity's central predictions. Across immense cosmic distances, both signals travel with essentially the same invariant speed, yet perhaps the most ambitious searches concern phenomena that have never been observed directly. Physicists hope that extremely energetic cosmic events might reveal subtle signatures of quantum gravity. Gamma-ray bursts are among the brightest explosions in the universe. Some release more energy within seconds than the sun will emit during its entire lifetime, because these photons travel for billions of years before reaching Earth. Even unimaginably tiny deviations from Einstein's predictions could accumulate into measurable arrival time differences. Space observatories such as the Fermi Gamma-ray Space Telescope have searched carefully for precisely these effects. To date, no convincing evidence has emerged that higher energy photons systematically travel faster or slower than lower energy photons through the vacuum. These null results are scientifically valuable. They eliminate entire classes of theoretical models while strengthening confidence in others. Sometimes the most important discovery is learning which possibilities nature refuses to accept. Researchers are also investigating whether dark matter or dark energy might indirectly influence the deepest properties of space-time. At present, no observational evidence indicates that either phenomenon changes the invariant speed of light. Dark matter reveals itself through gravity. Dark energy appears through the accelerated expansion of the universe. Both remain mysterious in their own right. Their relationship, if any, to the origin of fundamental constants remains unknown. Computer simulations have become another indispensable tool. Theoretical physicists construct detailed numerical models of black holes, neutron star mergers, quantum fields, and cosmic evolution. These simulations allow researchers to compare competing theories with real astronomical observations. Although a simulation cannot replace an experiment, it can reveal whether a proposed idea behaves consistently with known physics. Increasingly powerful computers have therefore become essential partners in modern scientific discovery. Across all these efforts, a common pattern emerges. Each new instrument extends our reach. Each new measurement reduces uncertainty. Each new observation strengthens or challenges existing theories. Yet almost every advance produces an unexpected consequence. Instead of closing the mystery, it often enlarges it. the more accurately we confirm Einstein's description of space-time, the more pressing the deeper question becomes. Why should reality possess this elegant structure at all? Every major observatory operating today contributes a small piece to that puzzle. None has yet uncovered the final answer. Perhaps this should not surprise us. History rarely advances through a single decisive experiment. Instead, understanding grows gradually, as many independent observations converge upon the same conclusion. Today, those observations have carried humanity farther than ever before. We have measured light crossing billions of light years. We have observed gravitational waves rippling through space-time. We have imaged the environment surrounding black holes. We have mapped nearly the entire observable history of galaxies. And still, one quiet question remains. Not how light travels, not how fast it moves, but why the universe itself is built around this extraordinary constant. Beyond that question lies the true frontier of modern physics, where even our most successful theories acknowledge the boundaries of current human knowledge. There is a quiet moment that arrives in every scientific journey. It comes after the observations have been gathered, after the equations have been tested, after the theories have been refined as far as present evidence allows. Beyond that point, certainty begins to fade, not because science has failed, but because it has reached the edge of what nature has so far permitted us to measure. This is where our exploration now stands. Throughout the past century, physicists have built one of the most successful scientific frameworks in human history. Relativity describes gravity across the observable universe with remarkable accuracy. Quantum field theory predicts the behavior of elementary particles with extraordinary precision. Together, these theories have transformed technology, astronomy, and our understanding of reality. Yet they do not fit together perfectly. And it is precisely within that gap that some of the deepest unanswered questions about the speed of light continue to reside. One of the greatest challenges concerns gravity itself. General relativity treats spacetime as smooth. At every location, the curvature of spacetime changes continuously in response to mass and energy. The mathematics is elegant. More importantly, it agrees beautifully with observation across planets, stars, galaxies, and black holes. Quantum mechanics approaches nature differently. Its equations describe probabilities, discrete interactions, and quantum fields whose fluctuations can never be completely eliminated. When physicists attempt to apply quantum principles directly to spacetime itself, familiar mathematical techniques begin producing infinities that resist straightforward interpretation. This does not prove that either theory is wrong. It suggests that both are incomplete descriptions of a deeper reality. Somewhere beneath them may exist a more comprehensive framework. Whether that framework preserves space-time exactly as Einstein described it, or reveals an entirely new picture remains unknown. This uncertainty immediately affects our central question. If current theories become incomplete at extremely small scales, then perhaps their explanation of the speed of light is also incomplete. Not incorrect, simply unfinished. Another major uncertainty concerns the Planck scale. This scale combines the speed of light, the gravitational constant, and Planck's constant into natural units where both gravity and quantum mechanics become equally important. The resulting length is unimaginably small, approximately 1.661035 meters. To appreciate just how distant this scale is from direct observation, consider a proton. Its diameter is roughly 10-15 meters. The Planck length is another 20 orders of magnitude smaller. If a proton were enlarged to the size of the observable universe, the Planck length would still remain microscopic by comparison. No existing microscope, telescope, or particle accelerator can resolve distances remotely close to this regime. This limitation is not merely technological. It may reflect fundamental physical constraints. Building an accelerator capable of probing Planck scale energies directly would require resources vastly beyond anything humanity can currently imagine. As a result, researchers must rely on indirect evidence. They search for tiny signatures that an underlying quantum structure of space-time might leave upon observable phenomena. So far, those signatures have remained elusive. Another unanswered question involves Lorentz symmetry itself. Special relativity assumes that the laws of physics remain identical for every observer moving at constant velocity. Countless experiments support this principle. Nevertheless, Several candidate theories of quantum gravity investigate whether Lorentz symmetry might be only approximately true. If spacetime possesses microscopic structure, perhaps tiny violations appear only at extremely high energies or over cosmological distances. Testing this possibility has become a major experimental effort. Astronomers examine gamma-ray bursts. Particle physicists analyze cosmic rays. Precision laboratories compare atomic clocks with astonishing accuracy. Every successful test places stronger limits on possible departures. To date, no convincing violation has been confirmed. That result is scientifically important. It tells us that if new physics exists, it must preserve relativity with extraordinary precision under all conditions we have been able to observe. The vacuum itself remains another profound mystery. Quantum field theory describes empty space as filled with fluctuating fields. Those fluctuations influence measurable phenomena such as the Casimir effect and the Lamb shift. Yet the same theory predicts an enormous vacuum energy density that differs dramatically from the value inferred through cosmological observations. This discrepancy is known as the cosmological constant problem. It is one of the largest unresolved disagreements between theoretical expectation and observation in all of physics. No accepted explanation currently exists. Whether this mystery has any direct connection to the origin of the speed of light remains unknown. Still, both questions concern the physical nature of empty space. It would not be surprising if future insights eventually link them. Dark matter introduces yet another uncertainty. Astronomers infer its existence because galaxies rotate too rapidly for visible matter alone to account for their motions. Galaxy clusters bend light more strongly than ordinary matter predicts. The cosmic microwave background also carries signatures requiring additional gravitating matter. Yet despite decades of searching, the fundamental nature of dark matter remains unknown. If dark matter consists of undiscovered particles, does it interact with space-time in completely familiar ways? Could it reveal previously hidden aspects of the vacuum? Current evidence provides no indication that dark matter alters the invariant speed of light. The possibility simply remains unexplored because the underlying substance itself has not yet been identified. Dark energy presents an equally profound puzzle. Observations show that the expansion of the universe is accelerating. Whatever drives this acceleration dominates the large-scale energy budget of today's cosmos. Yet its physical origin remains deeply uncertain. Some explanations invoke vacuum energy. Others propose new fields or modifications of gravity. None has yet achieved universal acceptance. Again, no evidence presently indicates that dark energy changes the local speed of light. Its existence does remind us that the universe still contains major components whose true nature remains hidden. Even the beginning of the universe raises unanswered questions. Our current cosmological model successfully describes the evolution of the universe back to an extremely early epoch. Beyond that point, certainty rapidly decreases. The conditions near the Big Bang almost certainly required both quantum mechanics and gravity simultaneously, because those theories remain incompletely unified. Our description of the earliest moments is necessarily provisional. If the speed of light ultimately emerges from deeper quantum gravitational processes, the earliest universe may hold important clues. Unfortunately, those clues are extraordinarily difficult to recover. The cosmic microwave background provides our oldest direct electromagnetic observation. Everything earlier remains largely inaccessible except through indirect inference. Perhaps the deepest uncertainty of all concerns explanation itself. Physicists often ask whether every fundamental constant should possess a deeper theoretical origin, but nature is under no obligation to satisfy that expectation. It is entirely possible that some constants simply define the framework within which every further explanation unfolds. If that is true, then asking why the speed of light has its specific value may eventually resemble asking why mathematics begins with its own axioms. The question is meaningful. The answer may simply terminate. Many researchers, however, remain optimistic. History encourages them. Again and again, questions once thought permanently beyond explanation eventually yielded to new principles. The motion of planets, the origin of heat, the unity of electricity and magnetism, the nature of atoms. Each seemed mysterious until a broader framework emerged. Perhaps today's constants will one day follow the same path. Perhaps they will not. At present, science cannot decide. There is a certain beauty in this uncertainty. Modern physics is often celebrated for the questions it has answered. It is equally remarkable for the questions it has revealed. The more carefully we measure nature, the more precisely we discover the boundaries of our own understanding. Those boundaries are not signs of failure. They are maps. They show future generations where exploration is still possible. Somewhere beyond today's theories may lie a principle that explains why space-time possesses its remarkable geometry, why information obeys a universal causal limit, why light travels exactly as it does, or perhaps the mystery will become deeper still. Whatever the answer, reaching it will require looking beyond the limits of today's observations toward the frontier where tomorrow's discoveries are waiting. Every scientific frontier shares one defining characteristic. It is not a place where knowledge ends. It is a place where reliable knowledge becomes increasingly difficult to obtain. The boundary moves slowly, almost imperceptibly. With each new telescope, each improved detector, each more precise experiment. What seemed unreachable to one generation often becomes routine for the next. Yet there are moments when progress slows, not because curiosity fades, but because nature demands tools that do not yet exist. The mystery surrounding the speed of light now rests at such a frontier. For more than a century, relativity has described the observable universe with extraordinary success. Quantum mechanics has explained the microscopic world with equal brilliance. Between them, these two theories account for almost everything humans have directly measured. And yet, they remain incomplete. They coexist remarkably well in most situations, but they refuse to merge into a single seamless description of reality under the most extreme conditions. Those conditions exist where gravity becomes overwhelmingly strong, while quantum effects cannot be ignored. The centers of black holes, the earliest fractions of a second after the Big Bang, perhaps the interiors of neutron stars at their most extreme densities. These environments are not simply difficult to reach. They may forever remain inaccessible to direct human exploration. Instead, astronomers must become detectives. They search for subtle clues carried outward by light, gravitational waves, neutrinos, and cosmic rays. Each messenger preserves a fragment of a story written under conditions impossible to reproduce completely on Earth. Future observatories promise to sharpen that story considerably. The next generation of gravitational wave detectors will be dramatically more sensitive than today's instruments. Projects such as the planned space-based observatory LISA are expected to detect gravitational waves with much longer wavelengths than those accessible to ground-based facilities like LIGO. Instead of observing primarily stellar-mass black holes and neutron stars, they will probe collisions involving supermassive black holes, compact binaries, and possibly signals originating from processes that occurred much earlier in cosmic history. These observations may not explain why the speed of light has its value. They could reveal whether spacetime behaves exactly as general relativity predicts under conditions never before observed. Even tiny discrepancies would be invaluable. Another powerful frontier lies in radio astronomy. The Square Kilometre Array, now under construction across Australia and South Africa, will become the largest radio telescope ever built. Its enormous collecting area will allow astronomers to map hydrogen throughout much of cosmic history, study pulsars with unprecedented precision, and investigate the large-scale structure of the universe in extraordinary detail. Each of these observations offers another opportunity to test the geometry of space-time and the propagation of electromagnetic waves across immense distances. Meanwhile, optical astronomy continues advancing rapidly. Future extremely large ground-based telescopes, with mirrors measuring several tens of meters across, will study planets orbiting distant stars, resolve stellar populations in remote galaxies, and observe some of the faintest objects ever detected. Combined with space telescopes operating beyond Earth's atmosphere, these facilities will extend humanity's observational reach farther into the universe than ever before. None of these instruments alone is likely to uncover a hidden explanation for the speed of light. Together, however, they tighten the constraints within which every successful theory must fit. Particle physics faces an equally ambitious future. Researchers continue discussing next-generation accelerators capable of reaching energies beyond those available at the Large Hadron Collider. Such machines would not approach the Planck scale directly. That remains unimaginably beyond present engineering. Nevertheless, they could reveal entirely new particles, new symmetries, or previously unknown interactions that reshape our understanding of the vacuum. History reminds us that major conceptual breakthroughs often begin with unexpected discoveries. When electrons were first identified, no one anticipated quantum mechanics. When radioactivity was discovered, nuclear physics did not yet exist. When cosmic expansion was observed, modern cosmology was still in its infancy. Future particle experiments may likewise uncover clues whose significance becomes clear only decades later. Theoretical physics will continue evolving alongside these observations. One of its central goals remains the search for quantum gravity, whether through string theory, loop quantum gravity, causal set theory, asymptotic safety, holographic dualities, or approaches not yet imagined. Researchers seek a framework capable of describing space-time under the most extreme conditions while reproducing the remarkable success of relativity where it has already been tested. Any successful theory must satisfy an extraordinary list of requirements. It must explain gravity. It must remain compatible with quantum mechanics. It must recover Einstein's equations in ordinary circumstances. It must preserve the precise experimental agreement accumulated over more than a century. And if it attempts to explain the origin of the invariant speed, it must also account for why every existing observation finds exactly the same value. This is one reason progress has been so challenging. Nature has provided remarkably little room for new ideas to differ from established physics. Every successful experiment narrows the available possibilities. In science, this is a sign of strength rather than frustration. A theory that survives increasingly demanding tests becomes more trustworthy. Yet history also teaches humility. Newton's gravity survived for centuries before Einstein revealed a deeper picture. Classical mechanics remains extraordinarily useful despite not being the final description of motion. Likewise, relativity itself may eventually become part of a broader framework whose low-energy behavior is indistinguishable from Einstein's equations. If that happens, future physicists may view our current theories much as we now view Newton's. Not wrong, profoundly successful within their domain, incomplete only under conditions where deeper principles emerge. There is another possibility that deserves equal attention. The search for deeper explanations may eventually reveal that the invariant speed truly is fundamental. No hidden mechanism, no microscopic derivation, no deeper layer from which it emerges. Instead, it could represent one of the basic axioms from which every physically meaningful description of the universe begins. Some scientists consider this outcome entirely plausible. Others suspect that history favors deeper unification. At present, evidence supports neither conclusion decisively. That uncertainty is not a weakness. It is an honest reflection of the current state of knowledge. Perhaps the greatest lesson offered by this mystery is methodological rather than physical. Science advances not by refusing uncertainty, but by defining it precisely. Centuries ago, people did not know whether light even possessed a finite speed. Today we measure that speed with extraordinary precision. We understand how it governs relativity. We observe it shaping galaxies, black holes, gravitational waves, and the expansion of the universe. The remaining mystery is vastly narrower than it once was, yet it is also deeper. The question has shifted from measurement to meaning, from velocity to origin, from observation to the architecture of reality itself. If future generations eventually answer that question, the consequences could extend far beyond light. A successful quantum theory of gravity might reshape our understanding of space and time. It could reveal why black holes possess entropy. It might explain the earliest moments after the Big Bang. It could illuminate the relationship between information and geometry. It may even redefine what physicists mean by a fundamental constant. Or the answer may prove simpler than anyone expects. Nature has surprised humanity before. It almost certainly will again. For now, however, the frontier remains exactly where every great scientific frontier has always been. Not at the edge of imagination, at the edge of evidence. Beyond it lies possibility. On this side lies everything careful observation has allowed humanity to know. And between those two worlds stands one quiet number, measured countless times, woven into every successful description of the cosmos. still waiting to reveal whether it is the beginning of the story or merely one chapter within a far deeper one. When we began this journey, the speed of light seemed like one of the simplest facts in nature. It appeared to be little more than a number, a value printed in textbooks, a constant measured so precisely that scientists now use it to define distance itself. It felt complete, almost ordinary. Yet the farther we travelled, the more that familiar certainty quietly transformed into something much larger. The speed of light is not merely the motion of a beam crossing empty space. It is woven into the structure of reality. It shapes the relationship between space and time. It defines how quickly information can travel. It governs the life of stars, the bending of galaxies, the evolution of black holes, and the history carried toward us by the oldest light in the universe. Without changing a single observation, our perspective has changed completely. We no longer see light simply as something that illuminates the cosmos. We see it as one of the principles through which the cosmos reveals itself. Along the way, we encountered one of science's quietest paradoxes. Humanity has learned to measure the speed of light with astonishing precision. We understand how it behaves inside atoms. We understand how gravity bends its path. We have watched it cross billions of light years. We have observed it accompanying gravitational waves from merging neutron stars. We have built theories that predict its behavior more accurately than almost any other description in science. And yet, beneath all of that understanding, one question remains gently unresolved. Why this speed? Not why light moves quickly, not why relativity succeeds, but why the universe itself possesses this remarkable invariant constant. The distinction is easy to overlook. Science often begins by asking how. Only much later does it begin asking why. Sometimes the second question proves far more difficult than the first. There is a quiet humility in recognizing that difference. Modern physics is frequently described as a collection of answers. In many ways, it is better understood as a map. Some regions of the map are drawn with extraordinary confidence: planetary motion, nuclear fusion, the evolution of stars, the propagation of light through space-time. Other regions remain faintly sketched: quantum gravity, the microscopic structure of space-time, the origin of fundamental constants, the true nature of dark matter and dark energy. Beyond those regions lies blank paper, not because nothing exists there, but because no reliable observation has yet reached that far. Blank spaces on scientific maps have always carried a special meaning. They are not invitations to invent explanations. They are invitations to keep exploring. History reminds us how often today's mysteries become tomorrow's foundations. The stars were once lights fixed to a celestial sphere. Later they became distant suns. The Milky Way was once thought to contain the entire universe. Later it became one galaxy among hundreds of billions. Space and time themselves were once separate absolutes. Then Einstein revealed them as different aspects of the same geometric reality. Each generation inherited mysteries that seemed almost permanent. Each generation also discovered that nature was subtler, more elegant, and often more surprising than expected. Perhaps the mystery of the speed of light will follow the same path. Perhaps future physicists will uncover a principle from which the invariant speed emerges naturally. Just as Maxwell united electricity and magnetism, or Einstein united space and time, or perhaps they will discover that the search itself has reached bedrock, and that some features of reality are truly fundamental. Today, we do not know, and there is something quietly reassuring about that uncertainty. Science does not become weaker when it admits the limits of present knowledge. It becomes stronger. Every confident statement in modern physics carries meaning precisely because researchers distinguish so carefully between what has been observed, what has been inferred, and what remains unknown. The mystery surrounding the speed of light illustrates that discipline beautifully. We have resisted the temptation to replace unanswered questions with comfortable stories. Instead, we have followed the evidence wherever it leads. Sometimes the evidence opened new doors. Sometimes it simply revealed how much farther the journey extends. If we step back one final time, another perspective begins to emerge. For nearly all of human history, the universe seemed impossibly distant. The stars appeared forever beyond reach. Today, although we still cannot travel to them, we possess something almost as remarkable. We understand the language carried by their light. Every photon arriving from a remote galaxy is a messenger that has travelled across oceans of space and rivers of time. Its journey obeyed the same physical laws that govern the sunlight falling across Earth's forests, mountains, and oceans. The same constant links the birth of galaxies to the warmth of an afternoon, the explosion of a supernova to the glow of a candle, the oldest observable light in existence to the atoms within our own eyes. There is a quiet unity in that realization. The universe does not separate the ordinary from the extraordinary. The same principles operate everywhere. The constants governing the larger structures in existence are the very same constants that shape the smallest events in everyday life. Perhaps that is why the question feels so compelling. If one number appears everywhere, understanding its origin would not merely explain light. It could illuminate something profound about reality itself. And yet, perhaps the greatest gift of this mystery is not the answer it promises. It is the perspective it offers. Every generation inherits a cosmos that appears almost complete. Every generation eventually discovers another horizon. The farther we look, the farther the horizon seems to move. That is not a sign that the universe is hiding from us. It is a reminder that knowledge is not a destination. It is a continuing conversation between careful observation and human curiosity. Long after today's telescopes have been replaced, long after today's theories have been refined or expanded, light will still be crossing the darkness between galaxies. Ancient photons will still be arriving from places so distant that their journeys began before Earth itself existed in its present form. Future observers may understand those travellers more deeply than we do now, or they may uncover mysteries we have not yet imagined asking. For the moment, one fact remains beautifully unchanged. Every glimpse of the cosmos reaches us because light continues its silent journey across space, faithfully carrying the history of the universe without revealing every secret of its own. And perhaps that is the deepest wonder of all. The more completely we learn to read the messages written in light, the more gently the universe invites us to ask one final question. If the speed of light is woven so perfectly into the fabric of reality, what deeper pattern gave rise to the fabric itself?